So in the branch prediction algorithm, if you recall, in our previous session, we talked about the control hazards. So these control hazards occurs because of the branch instructions, and we looked at certain solutions, that is stalling the pipeline is one solution. Another one is we assume that the branch is assumed not taken, that is, it will not be taken. And then we looked at the branch delay slots, but none of those solutions are really address the problem. So today we'll try to discuss the branch prediction. So this is the best solution to branch which induce the control hazards. Okay. So for a branch instruction in the branch prediction that predicts whether the branch is taken or not taken. If the branch is taken, then what is the target address? If the branch is not taken, then what is the target address? So that is required, the target address. Correct? So the prediction is then used to fetch the next instruction from the instruction memory based on whether the branch is taken or not taken. So we know that whether the branch will be taken or not taken, that will be, decided at the end of execution stage. Correct. So that's why the many instructions they stop their execution. So the branch in this branch prediction algorithm, the branch behavior is monitored during the instruction execution, the branch instruction execution. So the history data can influence the prediction of future execution of the branch instruction. So branches, the instruction execution has two tasks. One is first task is the condition evaluation. One ALU is used to find out whether the condition is true or not. That is the comparison instruction. And based on that comparison instruction, the second ALU in the execution stage that computes the branch target address. So in the branch prediction, the first task is finding the direction of the branch, whether it go back or it forward to the next instruction. So for that, there are different methods are there. One is the 1-bit saturating counter, and another one is the 2-bit saturating counter. So we'll see this. The basic idea of this branch direction prediction is if it is conditional jump, then there will be a loop. So backward will be there. If it is a unconditional jumps, then the forward loops will be there. So we look at this with an example. In 1-bit branch direction prediction, one binary bit is used to record the history of the branch during its execution. Right? So let us consider a simple C code with the condition or conditional branch. So for I is equal to 0 and I less than 4 and I plus plus. So inside that, another branch is there for j is equal to 0, j less than 4, and j plus plus. So for this, a simple code, C code, if you compile this code, it will give us the assembly code. But in this, the first for loop, okay, where I is equal to 0, that will be executed. How many times it will execute? From 0 to 4, so it will execute 4 times. It will also execute 4 times in the iterations, 4 times. Okay. So then let us see the actual outcome of this branch, and then we'll try to discuss the one bit branch direction prediction. Okay. So wherever you find the doubts, you please let me know. Yeah, Austin, that's correct. Austin, Jonas. Yeah, that's correct. So let us see the actual outcome, the branch outcome. For I is equals to 0, so then this branch will be executed. So how many times? For j is equal to 0, this branch will be, second branch will be executed. Let us say this one is the first one. So how many times for j is equal to 0, 1, 2, 3? Because the condition will be true here. So it will execute 4 times. Then when condition is 4, it becomes fail here. So the branch will not be taken. Control goes back to the instruction 1, the first branch instruction. Then I plus plus means I increase from 0 to 1. In the second iteration also, when the condition is true, this is the comparison statement CMP. And the target is, when this comparison is true, then the target is L2. The location, let us say label 2, will be executed. Okay. And if this CMP fails, then it goes to level 1. That is the target address. So for I is equal to 1 and j is equal to 0, okay, for I is equal to 1 and j is equal to 0, 1, 2, 3, the second branch will be taken 4 times. And this continues for the remaining iteration. So when I is equals to 3, okay, so these for I is equal to 3, j is equal to 0, 1, 2, 3 is condition. And for the fourth one, the condition fails. Okay. So then it goes back where I plus plus, that will become I is equal to 4. So the condition will be failed here. So at this point, both the instructions, branch instruction stops their execution. So 16 times the branches are taken and 4 times the branch is not taken. Correct? So here the assumption is, assume the branch is not taken. So in one bit prediction, when a new hardware is designed, in one bit prediction, it starts with the branch will not be taken. The first assumption is to record the history of this branch behavior in one bit saturating counter, branch direction prediction. The hardware is designed in such a way that it starts with a one bit history table. So in one bit history table, the entries in the history table starts with the 0. That means the branch is not taken, or branch will not be taken. This is the assumption, assuming that the branch will not be taken. So initially, it is assuming that this branch will not be taken. So that is the prediction. Okay. So in this prediction, let us say for I is equal to 0 comes to this branch L2, the hardware is predicting that. Okay. So this part is executed with one hardware unit, and this one is the second hardware unit which we built. Okay. So then at I is equal to 0, the hardware prediction predicts that for j is equal to 0, in one bit saturating counter predicts that it will not be taken. The branch will not be taken. It is the assumption, but actually the branch is taken. So when there is one wrong prediction compared to the actual outcome, then the bit 0 turned into 1. That means from not taken, I'm using the terminology here, NT means not taken and T means taken. So it inverts the bit from NT to taken and then compares the prediction with the actual outcome. So at j is equal to 1, the branch is taken and prediction is also taken. So there is a correct prediction. Then it assumes that in the future also at j is equal to 2, the branch will be taken. It predicts that it will be taken. And then during the execution, at third stage of the pipeline, when it decides that it will taken, then the prediction will be true. So in the history table, it maintains that one bit. So it says that after one wrong prediction, it inverts the bit. So let us see in this animation now. So it assumed that starting with the not taken, but actually it is taken. So it inverted it bit to taken. Then comparing this t with iteration 1 in actual outcome, it's true. Then predicting that in the future also it will taken. And after execution, if it is taken at iteration 2, the prediction is correct. So at iteration 3, it assumes that the hardware predicts it will be taken and it is taken, suppose. And at the fourth iteration, the hardware predicts that it will taken based on the previous history. But in actually, it is not taken. So there is one wrong prediction. So then it inverts its status in storing the history table from taken to not taken. For j is equal to 0, it assumes it will not be taken. But actually, it is taken. So the same prediction process continues until this loop, these branches are executed for 4 iterations of the global branch. So now tell me, in this hardware predictions, how many right predictions are there and how many wrong predictions are there? Yeah, because of this hardware prediction, it won't wait until it enters into the execution stage. Because at the end of the execution stage only,